Okay, in this video, we're going to work through the practice exam. I decided not to do it during class because we need to keep the same pacing with respect to the new material. So I'm going to make this video going through the practice exam. So first, let me share my screen. So some of these I'm going to work somewhat quickly through, like the ones that are more computational, like problems 2 and 3, I'll just kind of work through pretty quickly. So let's just start right now. So this is number 1. I'm going to write the problem down. So I'm going to assume that you're going to have the PDF opened up and working along with this video. So I'll just write some of the details down. So we have these sets A and B. A is this interval from 0 to 2, including 0 but not 2. And this B is the set -1, 1, including 1 but not -1. And we want to find the union and the intersection. So the best way I find to do this is to draw 2 copies of the real line parallel to each other, and then we're going to plot. We're going to plot each set. So this will be A, this will be B. So maybe we have -1, 0, 1, 2. So -1, 0, 1, 2. And okay, so let's see. So A is from 0 to 2, and it'll be a closed circle here because 0 is a point in the set, and it'll be everything up to 2, but not including 2. So we'll have a solid circle or open circle. And then B is it starts at -1, but it doesn't include it, and then it goes all the way up to 1. And then from here, we want to find out what the union and intersection are. So the union, I think we can get pretty easily. So let's just write that down. So it's just everything that's in both sets. So it's like you kind of just project on each line, and this is like the extent of it. This from this dotted line to this dotted line. And you can see that goes from -1 to 2. So -1 to 2, but it doesn't include those. But now let's find the intersection. So the intersection is a little bit trickier, but it's not too bad. So we just take, we look at all these endpoints and we project down like this. And so we take the left endpoint of A, and then we take the right endpoint of B, and then it's going to be this part right here. This is the overlap of these 2 sets. This right here. So it's going to be this interval right here, whatever that interval is. And so the interval is just from 0 to 1. And it's going to include 0 and it's going to include 1 because 0 is a point in A and it's just a point in B. And then the same thing with 1. 1 is a point in A and 1 is a point in B. And then it's everything between. So it's going to be 0 to 1. So if we look at our options, we can see that if I did it right, B is the answer. So just circle option B. Now let's move on to 2. So this one I'm just going to run through quickly. So we want to simplify this so that there are no negative exponents. We want to cancel terms, any terms that we can, and then make sure we flip the terms into the numerator or denominator so that the negative exponents go away. So first of all, these coefficients, these numbers right here in the front, we can cancel. So 6 has a factor of 2, so this will be 3. And then so the 2's cancel, in other words. Now this negative exponent, the absolute value of this is less than that. So what we want to do is we want to bring this up into the numerator. Oops. And then now what we want to do is do the same thing with b. We want to bring that into the denominator to make it positive. And then we can combine the terms. So if we have a raised to some power, a raised to another power, you just add the law is, or the rule is, or the property is that you add the exponents. So you have a to the 7th, and then you have b to the 11th. That will be the answer. So this is number 3. We have 2 fractions which we want to multiply. So the 2 fractions are as follows. So we have 4x over x squared minus 36. And then we're multiplying that by x plus 6 over 16x. So we'll just multiply the numerator by numerator, denominator by denominator. We get this. 6. I'm going to put the 16x in the front. Oh, minus right there. And now what we can do is we can cancel the x's, and then we can cancel a factor of 4. So yeah, I'll just do that first, and then what we're left with in the numerator is x plus 6, and then the denominator is going to be 4x squared minus 36. And then we can factor the x squared minus 36 as follows. So we have 4 times x plus 6 as x minus 6. And then this x plus 6 cancels. So this x plus 6 cancels with that x plus 6. And what we're left with is 1 over 4 times x minus 6. So for the next problem, we have, let's see, it's number 4. So number 4 is that we're given the following quadratic equation, and we want to solve for x. So first we gotta, and we're told specifically how to solve for it. We're not supposed to use you know, quadratic formula or anything like that. We're told that we can do this by factoring. So if that's on the exam, I wouldn't give you credit or I wouldn't give you full credit at least if you solved this by using the quadratic formula, as you're told specifically to solve it by factoring. But before we can solve by factoring, we have to simplify this as much as we can. So what we're going to do is subtract 2x from both sides. So that will give us this. And then I can subtract an x from both sides. And that will give me this. And then finally, I can subtract 3 from both sides. This doesn't look right though, actually. Did I screw something up? No, I did not. So if I subtract 3 from both sides, I get a negative 10 over here. You don't have, on the exam, you don't have to do all these steps individually. You can just do it all in one fell swoop, so you can go from here to here. That's fine. As long as you're able to keep track of it in your head, you can do all 3 subtractions at once. That's perfectly fine. So at this point, we can factor it. Because there's you're unlimited time. You have limited time, so I would be fine with that. If you can't keep track of all things like that, of course, do the steps out individually. So we can factor this. So we have to look at factors of 10 whose sum is +3. So you have factors. The factors are 2 and 5 and 1 and 10. Modulo, like plus or minus, there's signs you have to worry about. And it's going to turn out that if the right combination is this. And if you FOIL it, you'll see that you do get this back right here. So the x goes to x, you get x squared, and you have x times -2x, so that gives you -2x. But then you have a 5x over here, so 5x minus 2x gives you the 3x, and then the 5 times the -2 gives you the -10. So this is a correct factorization. It's the right factorization, and then this will imply that x is equal to -5, and x can be, maybe I should say that, or x can be 2. Those will be the solutions. So now we're on to number 5. And we have to solve the following equation for x. So we have this fraction. So first of all, we can make an observation that x cannot be plus or minus 1. These values are not allowed. So whatever values we get, we got to make sure they're not these values, right? Remember that problem of that is, if you assume x is a solution to this, then you will get certain values of x, but they're not. Well, yeah, the idea is if you assume that this equation holds, you'll get values of x, but those aren't necessarily the solutions of x. You have to go back and check. Because you can, I think we saw an example where we introduced what's so-called extraneous solutions. These are values that aren't actually solutions. So it's kind of what's the word? I can't even think of the word, but it's an incorrect term actually to say there's extraneous solutions. They're just not solutions at all. So if at the end you get x's plus or minus 1, you know that you have to rule those out. They are not actually solutions. But let's just not even keep that in mind for now, because maybe that won't happen to us. Maybe we won't have to worry about that. So what I would do for this one is I want to get rid of these fractions. And the following thing that I'm going to do is potentially where we could introduce values of x which are not actually solutions, because we're going to change the equation a little bit. So we have to be careful. But the idea is I want to get rid of the fractions. So I'm going to multiply by x squared minus 1, which of course can be factored as follows, right? And the reason why I want to multiply x squared minus 1 is because I have the right cancellation to happen on both sides of the equation. So if I do that, I will get x squared minus 1 times x minus 1 is equal to x squared minus 1 times 1 over x plus 1 plus 2. So as I noted here, x squared minus 1 can be factored this way. So x squared minus 1 and then times 1 over x. That 1 over x cancels with the 1 over x, or just the x minus 1. Sorry, the 1 over x minus 1 right here cancels with this x minus 1 here. So on the left-hand side, all we'll be left with is the following: x plus 1. Now I'm going to distribute the x on the right-hand side. I'm going to distribute the x squared minus 1 through. So I get x squared minus 1 times this fraction, and x squared minus 1 times the 2. When I multiply the x squared minus 1 with this fraction, that 1 over x cancels with this factor right here. So what I'm left with is the x minus 1. So I'm left with x minus 1 plus the 2 times this thing right here. And I'll just distribute it through to get 2x minus 2. And at this point, I can simplify a little bit. So this x cancels with this x, and then I can subtract the 1 from both sides. So I get 0 is equal to, so if I subtract 1 from both sides, well, first of all, I get -1, -2, so it's -3, and then I'm subtracting 1, so it gives me -4. So I get 2x squared minus 4, right? So let's just recap. This x cancels with this x. This -1 cancels with this, or this -1 right here combines with this -2 to give me -3. And then right here, I'm gonna I have this +1, so I need to subtract 1 from both sides. That's how I get. So it's -1 minus 3. So that's how I get -4 at the end. I can divide by 2. I get that, and then actually let's not even write it like that. Let's write it like this. So we get x squared is equal to 2, and then I can take the square root. So it's plus or minus square root of 2. So I multiplied by x squared minus 1, but it turns out I didn't actually introduce any values of x which are not solutions. So this will actually be the solution right here. I didn't have to worry about that. I didn't have to check to make sure. You can just plug in, you can plug in plus or minus square root of 2 into the original equation, and you will in fact see that they satisfy the equation. But I'm not going to ask you to do that on the exam because that's just too much. All I would ask is that you just be cautious when you go through this procedure right here. At the end, you'll get values of x. Just check to make sure that they make sense. If they make sense, then just leave it. But then if they don't make sense, point it out. Say these aren't actually solutions. These values of x are not actually solutions, and point out which values of x are solutions. In this case, all the values of x that we deduced are solutions. So we don't have to worry about that. So that's number 5. Let's move on to 6. So we want to find, so we have this inequality, we want to solve for it, and we want to express the solution in terms in interval notation. So luckily for us, this is already factored. And we're going to do this by making a sign table. So first of all, before we go off and straight away do that, let's know that we can actually simplify things a bit. So this factor, so remember, well, first of all, so this factor right here, no matter what value of x you plug in, it's always going to be positive. So this doesn't really determine the sign of overall expression. It does, because it doesn't change. It's always positive. These ones, these two right here, these ones are they're going to be flipping back and forth depending on what value of x is. So we have to keep track of these. These will determine sign of overall expression. Oops. Kind of sloppy, sorry. So when we construct our sign table, we don't need to have 3 rows, one for this, and one for this. We only need these 2 pieces right here. This one won't matter a whole lot. It won't affect the sign. Now, the principle we need to keep in mind is the following in order to solve this inequality. That is, a product of 2 numbers, namely x minus 3 times x plus 2, these 2 numbers, it will be positive if and only if they have the same sign. So we need to look for in our sign, quote unquote sign table, we need to look for those columns where they both have the same sign, whether they're both positive or they're both negative. So let's do that. So we have let's not even write it. We know we don't need to write sign of. We'll just write the factor, and we know that we're trying to compute the sign. So we have x minus 3, x minus 2, and then oh no, x plus 2, I think it was. And then the overall sign. So we got to divide it up like this. Now, the number of columns is going to depend upon the number of places where the sign could potentially change. And that's going to be the roots of this expression. So sign changes occur at roots. I should say in parentheses, possible sign changes, not guaranteed. The sign is not guaranteed to change at the root. That is when you move from the left to the right of the root. So yeah, let me just point this out. Let me just say possible sign changes occur at roots. So first of all, I just want to say I'm writing a lot. You don't have to write all of this stuff right here. You know, because I'm just trying to be thorough in the explanation. But you know, you don't have to point out that this doesn't really determine the sign. You don't have to write the fact that this sign changes occur at the roots. You can just take those as givens. You can just assume those. So you can go right to constructing the table because you know I want to make sure you have time to do this. So don't worry about writing all this down. I just want to point this out since we're going through. This is supposed to be an instructive video. It's not just here's the solution, but how do we get the solution? So you can go from here right to making the table. So the sign change. So the roots of this expression are x is 0. Let's put them in order. So this will x plus 2 will give me minus 2 as a root. X minus 3 will give me plus 3, and then the x squared will give me 0 as a root. So these are the roots. So we have like the real line is divided into 3 pieces, each piece corresponding to a root. Now, I did say that this doesn't determine the sign, so I don't need to look at its sign over these intervals because it's always positive, but I still need to keep track of what is the root of it. What is the root of x squared? The root or the 0 of it is, namely, it's 0 itself. So I need to take into account the roots of the whole expression. So I basically have, I think I'm making the table a little bit different than I normally do. So I have a copy of the real line up here. So I have the roots, which are -2, 0, and then 3. So this is -2, 0, and 3. So these are the columns. I want to look at the sign of the expressions over this. So again, you don't have to write all this down. You can go right from this inequality. You can just make a note of its roots, and then right here you can go right to this to determine the sign. So to determine the sign, we're going to take a test value from each interval. So we have this interval, this interval, this interval, and this interval. So we have 4 intervals. So a test value from here might be, say, -3. Just take -3. So if x is -3, we have, let's look at the sign of, let's just worry about the sign of this thing first. So x is -3, that will give us -6. So over this interval, we have negative. Test value between -2 and 0 would be -1. When x is equal to -1, x minus 3 is -4, so it's again negative over here. Now when we're between 0 and 3, a test value could be 1 or 2, it doesn't matter. We'll just take 1. So when x is equal to 1, you have x minus 3 is equal to -2, so it's negative again. Finally, over here though, when we're looking at 3 and beyond, the test value would be, say, 4. So if x is equal to 4, x minus 3 would be 1, and that's positive. So it's negative, 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 positive. Now let's look at the sign of x plus 2. When x is -1, when we're in this interval right here, sorry, when x is equal to -3, x plus 2 is equal to -1, so we're negative. So here we can immediately fill in this, the product will be positive. So that's one of the intervals we're interested in when they have the same sign. What about over here, -2 to 0? So when x is equal to -1, say x plus 2 will be +1, that's plus, so the overall sign is negative, so we're not interested in this interval. We want the product to be positive. So now we're over here, when we're between 0 and 3, say x is equal to 1, x plus 2 will be 3, and that's positive again. And then when you are beyond 3, say when x is equal to 4, x plus 2 is 6, so that's positive. So this will be a negative here, and this will be a positive. So we actually only care about this and this. These are our two intervals where the whole overall product is positive. So now, one thing you have to be careful about is that so the intervals are going to be from, let's just write it out, -infinity to -2. I don't know what I'm going to put a square bracket or parenthesis here, but I'll leave it blank. Union this other interval. Again, I don't know if it's going to be square bracket or parenthesis. That's what we're going to have to determine. So do we have square brackets or parentheses here? Well, the answer is no, because you have to go back to the original inequality. The inequality is strictly bigger than 0. So if x were -2, you would have that this expression right here is equal to 0, and 0 is not greater than itself. So you can't include the roots. So you got to put close the open parentheses. So this is the answer right here. This is the solution set. So yeah, I know this might seem like it took a while to go through this. Like, how can I go through this on the exam? But as I said again, you don't have to go through all this explanation right here. You can just start with the inequality, quickly write down the roots, write down your real line, chop it up according to the roots, take test values, and then just fill in the table and then get that. So that it should be a fairly quick problem once you've done these a few times. You don't have to go through all that explanation, but I just wanted to go through it for the benefit of those who are still maybe struggling with it a little bit. So that was number 6. So let's move on to number 7. So number 7 is that we're given 2 points. It's two-part problem. We're given 2 points, and we want to find, in the first part, we want to find the line passing through the points. So, and then the next problem, we want to find a line parallel to the one we find in part A, and it passes through a specific point. Well, let's just worry about getting the line in part A first. So we're given 2 points, so that means we can calculate the slope. So the first point is -1, 4, and the second point is, Q, which is 5, 2. So let's see. So we have to take the slope is the change in y over change in x. So the difference in the y coordinates. So for example, you could do 2 minus 4, and then the difference in the x coordinates. Making sure you start with the same point. So we started with Q. So we took 2 minus 4. So now we have to do 5 minus -1. So the top will be -2, and the bottom will be 6, and then we'll get 1/3. I'm not screwing these up. So this is the slope, and now we have point and a slope, so we can find the equation of the line. So you can either choose this point or this point. It doesn't matter. So I'll just choose Q. So it will be y minus 2 is equal to the slope, which is -1/3, oops, times x minus 5. And then I simplify, so I distribute, I get -1/3 x plus 5/3. Now I have to add but I can't figure out this -2 here, so I have to add 2 to both sides. Now I have to get a common, I need to write this, I need to get a common fraction, so this will be 2 can be written as 6/3, right? So this will be, when I add these two fractions, 6/3 and 5/3, I get 11/3. That's the answer right there for part A. So now for part B, I want a parallel line passing through a given point R, and R is 3, 5. And if you remember, there's a fact about parallel lines, and it says that two lines are parallel if and only if they have the same slope. So a slope of desired line, the line which we're trying to, whose equation we're trying to find, is also -1/3. So I have a point and I have a slope, and I can just do the same formula. So it'll be y minus 5 is equal to -1/3 x minus 3. And then I just go through the same simplification. So I distribute the 1/3 through, I get 1/3 x. -1/3 times -3 will be +1, and then I'm adding a 5 at the end. And so this will be, once I simplify it, should be that at least. So that should be the answer right there. So we use the fact, for the part B, we use the fact that two lines are parallel if and only if they have the same slope. The slopes are the same. But there's another fact about perpendicular lines, which you should know. So two lines are perpendicular if and only if. So let's say M2 is equal to -1/m, where obviously M1 is the slope of the one line, M2 is the slope of the other line. So these are the slopes of the two lines you're given. And this says this is the relationship between their slopes. So know that one too. That may or may not come up on the test. I don't know. Now, so that answers parts of problem 7. Let's move on to number 8. This is, we're given equation. We're told that it's this equation of a circle, and we want to put it in standard form and identify its center, and identify the center of the circle and the radius. So to do that, I'm going to put this constant term on the left-hand side or the right-hand side, and then I'm going to associate the x's and the y's. I'm going to put all those terms together. So x squared plus 4x, and then y squared plus y squared minus 6x, or 6y, and that's going to be equal to -12. So I need to complete the square on this, and then complete the square on that. So to do that, I take half of the coefficient of x term, and I square it. So I get, what I'm doing is 4/2 squared. And then I have this complete the square over here. So I take half of the y term coefficient, add that in, so it's -6/3 squared. But if I added this term and this term on the left-hand side, I have to add those on the right-hand side. And I'm just gonna do the arithmetic that I didn't do right here. So this will be 2 and it'll be squared, so it'll be 4. This will be 3, -3, and then I square it and I'll get 9. So now I can factor this, and then I can factor this. So this will be factored as, well, I guess if you want to just also do that simplification there, leave the sign. So this will be, yeah, it'll be 4, and then this will be y minus 6y plus negative 3 squared. Don't get rid of the sign, because then it won't be clear what sign you need to have in the factorization. So we'll simplify this. So this will be 13. It'll be 1, and then this now I can factor. You don't have to do this step if you don't want to. That's fine. You can just factor it right here. But if it isn't clear because you have these fractions, that's fine. You can simplify it in this way, but make sure you have that negative there. You need that negative. So this will be plus 2, x plus 2 squared. This will be, and this is why you need to keep track of your negatives, because you'll have a y minus 3 squared. So center is equal to negative 2, 3, and radius is equal. So this is, remember, the equation of the circle is that you have r squared on here. But if r squared is 1, r itself is 1, so we don't have to worry about that. If it were, say if you had the right hand side were 2, that would imply the radius is equal to square root of 2, because this would be your r squared. But we're not in this case, but I'm just saying, if that were the case, if you like did all the arithmetic and you ended up with 2 on the right hand side, that would be your r squared value, and you would need to take the square root to find r. So that completes number 8, and then we have number 9. Wait, I need the graph of this. Hold on. Let's see. So I need these. So we're working on number 9. So we have this piecewise function. We want to evaluate it, and we also want to identify its graph. So these are the options for the graph. Maybe this is a bad idea. I don't know, I'll go like this. Anyways, so for this one, yeah, this was dumb actually. Hold on, this was dumb. Let me just do the graph afterwards. So first of all, let's all right, let me just copy it down. Yeah, I'll just redraw the graph, and then I'll point out what option it is. So this is our piecewise function. So first of all, we want to evaluate it at a couple numbers. So first one is -1. So -1 is certainly less than or equal to 1. So that means we have to evaluate it according to this definition right here, this first definition. So we plug -1 into x squared, we get that. The next value we want to calculate is 1. So x again is less than or equal to 1, so we have to evaluate according to x squared. So we get that, and we get so we plug in 1 to x squared, so 1 squared is 1. And now we're at finally the last value that asked you to calculate, which is f of 2. So in this case, 2 is greater than 1, so we evaluate according to the second definition. So we get 2 plus 1, which is 3. So there's this, bonus question, and for right off the bat, from these calculations alone, we can conclude that F is not injected. I don't know if I'm really going to throw a bonus one question on the exam. Maybe I will. I don't know. But for the practice, at least I did. So it'll be clear from both the graph and this calculation here that F is not injective or one-to-one. So now let's try it. Let's plot this function. So, or get a rough plot of it, at least rough sketch. So from up to 1, really 1 is where the behavior of the function is going to change. So up to 1, so anything from -infinity to 1, it's going to look like our usual parabola. So open up like this, maybe, and it's going to be a solid circle here, because the definition says you look like a parabola if you're less than 1 or equal to 1. So it's less than or equal to 1. So you look like a parabola from -infinity up to 1. So then on the left of 0, we're going to look like the rest of the parabola. And then at 1 is where it changes. So at 1, now it becomes suddenly a line. And if you, so this is the value, this is the line. So you have the line that goes to that origin right here. It's going to be shifted up 1 unit. So it's going to be shifted up. Did I do this right? Maybe I didn't even do this right. Oh yeah, I did do this. Okay. So it's going to be shifted up 1. So if you take that line that goes to the origin like this, you shift it up 1 unit and it goes here. So you got this line that goes like this now. But I don't care about all of the line. I only care about this part right here, right? Up to 1, because everything, I don't care about the graph of x plus 1 to the left of 1. So I don't need this piece right here. So let me erase most of that. So I don't need all of this piece right here. I'm not going to try to erase it all though. I only care about, so the line goes to like here, like that. But I really only care about what it looks like at 1 and beyond. So at 1, it's going to have a solid circle because according to the definition, the graph of f of x does not look like the line x plus 1 at 1, because it only evaluates to this line if x is strictly bigger than 1. So there's going to be a solid circle right here, and then it's going to look like the rest of the line. So if you look at your options, then it should be clear that the answer is B. Okay. So now we have, that's problem 9. So let's move on to 10. This one I think I need to open them up. I do need to open them up both sides, side by side. So I don't know if there's really a way of doing this. Oops. So the problem is we want to determine, I need to make a copy of this actually. Then I need another one. So let's look at the graph. So here's the graph, and we want to determine some information. So we have the graph of f and we have the graph of g, and we want to determine some information about the two functions based on the graph. So f is the red line or the red curve, and G is the blue curve. And the first question is, how is f of 0 related to f of how is f of 0 related to g of 0? So we're looking at the two functions evaluated at x equals 0. So remember, the g of x or f of x represents roughly the distance from the function to the height. It's like the height of the function above or below the x-axis. So we want to know which one's higher above the x-axis, which one's larger. Well, if we look at this, we see that the graph of f is higher at x equals 0 than g. So we could say this: f of 0 is greater than g of 0, so implies f of 0 is larger. Because we're looking at what function is higher above the x-axis, or if they're both negative, which one's closer to the x-axis. So that answers the first part. Now the next part is, for what values of x do we have that f of x equals g of x? And so remember, there was the one time when we were looking at we were trying to interpret. There's that one section on interpreting inequalities and equations. And so one way of interpreting an equation is that you're looking at all the points where the two expressions, when you graph them, their graphs intersect. So we're looking at f of x equals g of x, and we want to look at all the points where the graph of f intersects the graph of g. So that if you look at the graph, it's kind of clear, I think, that they intersect at -2 and then 2. So and they, just by inspection, they intersect at plus or minus 2. So now again, we have an inequality, just as with the equation that has this interpretation in terms of the graphs. We have this inequality and has an interpretation in terms of the graphs. And we just want to know where is the way of, so we want to find the values of x for which this inequality holds. This expression is less than this expression. And that has the interpretation of the graph of g being above or at the same height as g of x. So certainly for equality, we want, and so first of all, we want to express this in interval notation. And so in those intervals, we should include -2 and 2, right? But now it won't be between -2 and 2 because f is greater than or equal to g of x. So it's got to be outside. So right here, the blue line, the blue curve, that's g of x, or that's just the graph of g, and that's above the graph of f. So if you inspect the plot, you can see that this is 1, 2, 3, 4. So the values of x, which the solution set to this inequality is -4 to -2, union 2 to 1, 2, 3, 4. Well, I guess they don't really. All right, so this is kind of ambiguous because the graph of g stops short of f. So 2, 3, 4. If you put down 3, that's fine. Or if you put down 2, 4, I would accept either one. Like if you just assume, well, maybe it goes a little bit past to here. But the point is that it's like the solution set to this inequality is a union of these two intervals, or this interval and that interval. Either one, I would accept either one. I guess the picture is technically kind of incomplete. Since I mean, it's showing that they're not even defined on the same domain, right? The domain of G is up to 3, and the domain of F goes beyond up to 4. So I'd accept either one. So now we have this final inequality. And this is where the graph of F is strictly larger or strictly higher than the graph of G. So if you just inspect the graph of G, the graph of F is higher when it's between -2 and 2, but it can't be, we've already determined that the two functions equal at x equals 2 and 2. So we can't include those. So it's got to be between -2 and 2, not including them. So that's the solution for that. So that answers question 10. Now let's move on to question 11. So we are given some function from the reals to the reals. And then G is another function from the reals to real, that is some transformation. I don't need the thing open anymore. So G of X, G is some transformation of F. And I specifically tell you what kind of transformation it is. So we want to figure out the formula for G of X in terms of F of X, given the description of its transformation. So we're first told that G of X is a horizontal shift to the left by 2 units. So how you do that is you take F and you evaluate it at X minus 2. That will give you the shift to the left by 2 units. Sorry, no, it's got to be plus 2. See, I even screwed up myself. Remember to figure out whether so the horizontal shift was always the most confusing transformation. It's like, does plus correspond to move to the right or moving to the left? And remember, the way to figure it out is always just use your example of x squared and just think about transformations of that to the shifting. So remember, transformations are rigid motions. So I mean, horizontal shift, not every transformation is a rigid motion. There's stretching and scaling. That's not rigid. But horizontal shift and vertical shift at least are rigid motions. So if you can keep track of how one point moves, you know how the rest of them move. So if you have, for example, if you have that the graph opens up at this point right here, say 2, how do you describe, so this first graph is x squared, and this other graph is going to be called, I don't know, h of x. Well, how do you describe this in terms of x squared? Well, figure out where the intercept's going. The intercept's going from 0 to 2. So I need to, in order to figure out what h of x is, I need the value, I need it to be that when I plug in 2, I get 0, right? Because that's my new intercept. Well, really the only way that can work is if I subtract off 2. Now, if I plug in 2, I get 2 minus 2 is 0, squared and 0. So I see that the intercept works. So in order, what this suggests is that moving to the right, I have to subtract off the number. But if I want to move to the left, I have to add the number like I'm doing here. So that's how I figure it out. I just look at an example and think about transformations of it, and specifically look at where the intercept is going. So we're told that G of X is a horizontal shift to the left by 2 units. That means I have to add 2. We're told that it's a vertical stretch, so that is I have to multiply on the outside by the function. I have to multiply by the number they're telling me, so 3. So this will ensure multiplying on the outside of the function rather than on the inside will ensure that all the y values, so remember f of x represents the y value. It gives you the y value. You plug it, you give an x value, you plug it into f of x, and that will be your y coordinate when you're thinking about the graphical function. And in order to stretch things vertically, I need to multiply my y values, namely my f of x values. So I have to multiply on the outside, and that will increase. Multiplying by 3 will basically, if my function's positive everywhere, if I multiply by 3, it will increase, it will triple all them y values, basically. It's going to triple all of them, make them bigger, so it's going to stretch it vertically. So that's why I multiply on the outside by 3. And then finally, we're told that G is a vertical shift 5 units downwards. So I need to move all the y values down. So I have to subtract by 5. So the vertical shifts are a little bit easier, because if you want to move up, you add the number. If you want to move down, you subtract the number. It's more intuitive. So this is how you describe G in terms of f. So looking at our options, it appears that C is the answer. Okay, so now let's look at the final problem. So I'm given two functions. F of x is equal to 5x plus 3 over 6x minus 2, and g of x is equal to 2x squared. So I haven't really specified their domains. So we're going to compute compositions. Now you remember, strictly speaking, in order to compute the compositions, you need the domains and the codomains to match up. But you can't just plug the function into the other one willy-nilly. You have to make sure that the domains and the codomains match. So, but for the sake of just getting used to how to actually compute the composition itself, we're not going to worry about that until we get to part 3 and 4. So for part 1, I want to compute f composed with g at x. So by definition, that's this. So you feed x into g, and then you feed that into f. So you feed x into g to get g of x, and then you feed g of x into f. But g is just 2x squared. And now I'm going to plug in wherever I see an x in the formula for f, I just replace it by 2x. So it's 5 times 2x squared plus 3 times 6 times 2x squared minus 2. And you could just leave it like this. I don't care. If you want to multiply the 5 and the 2 and the 6 and the 2, that's fine. You can do that. But you don't have to. This is good enough. So all I really care about is, are you plugging things in the right parts? Are you plugging the formulas in the right areas? That's all I'm worried about. This is just arithmetic at this point, which hopefully at this point we can all do for the most part. So now I want to do g composed f at x. So by definition, that's you feed x into f, and then f of x into g. So it's equal to this. And then f of x is equal to 5x plus 3 over 6x minus 2. Now you have to look at the formula of g, which is just 2x squared, and wherever you see an x, replace it by this fraction right here. So we get 2 times 5x plus 3 over 6x minus 2 all squared. And again, you don't have to FOIL this. You don't have to square the numerator and square the denominator. If you want to and you have time, that's fine, but that's not really what I'm interested in. So that's part 2 and part 3. So for part 3, I realized I'm not sure if there's some notation I'm using here. I'm not sure if I actually explained it. I thought I did, which is why I wrote it down in the problem, but now that I'm thinking about it, I'm not sure I did. So for part 3 and 4, I want to basically know, do these functions have inverses? And if they do, find them. So in it, I'm now specifying a domain for the function. So I not only do these functions have rules, but now I'm telling you what the domain is. So in part A, I wrote this: R \1/3, and I wrote R \5/6. Where remember, this is the set notation, the bracket. So this is a set consisting of just a single number. So what this number here is, what this notation is just a set difference. It's not that bad. I'm just going to tell you really quickly what that means. So if I have two sets A and B, I can talk about the so-called A minus B. I can talk about subtracting a set. And how you define it is the following: it consists of all X such that X is in A, but X is not in B. So it's like you have A and you're taking that part of that's B away. So in this case, I'm only subtracting off a single point from the set. So let's think about just more abstractly. So I have some set A, and then I have maybe some set here B, and then A minus B. So B is this guy right here. A minus B. Can I fill it in? I wonder if I can fill it in. I don't know if I can. Why not? Because I don't have these matched up perfectly. And it will bleed out. I don't even know if there's that tool. Let's do a different color. How about that? That'll make it clear what's going on. So B is all this right here. And A minus B, or A set difference B, is all this here outside of it, but still in A. It's everything that's in A, but not B. So in other words, you're taking this red part out, you're subtracting it off. So R, for example, R set difference 1/3 is basically you're taking the real line and you're just taking the point out 1/3. And I'll explain to you why I'm doing that in a moment. So another way of describing this set is the following. I'm just literally taking 1/3 away, and I can describe it as this. So here's another way of thinking of, in this case at least, the set difference. These two sets will in fact be equal. Because the set on the right-hand side, so by definition, R minus the set containing 1/3 is everything that's not 1/3. Well, this set right here on the right-hand side is just the same exact thing. It's everything in the real line, on the real line, except 1/3. That's why I have these open parentheses right here, because I'm taking that point out. So that's all that means. And why do I have to do that? Well, I have to take out 1/3 because, so let's look at our function. F goes for, I claim that it only makes sense as a function from this set to this set. That is, you can't define the function f on the whole real line. Why? Well, remember the rule for f. F is 5x plus 3 over 6x minus 2. If you plug in 1/3, you're going to get 6 divided by 3. Well, let's just plug it in. Let's just naively plug it in and see what we get. So you get 5 times 1/3 plus 3, and then you get 6 times 1/3 minus 2. So the top, you'll get 5 over 3 plus 3. But 3 can be written as 9 over 3. And then the bottom, I get 6 divided by 3 is 2 minus 2. Top, I'll get, but it doesn't really matter, it's 16 over 3. But I get 0, the denominator. So I can't plug in 1/3. That's why I have to take the point away. And then if I take a point away here, the 5/6 is going to be the point that's missed. In other words, you're going to miss a point. There's going to be a point in the codomain that doesn't get mapped to. So now you know, so for the test, you know what this means. R minus or R set difference 1/3 means literally just take the point 1/3 out of the real line. That's all. And if you don't like this notation, you can just think of it in this terms of the union of these two intervals. So now, as a function from those two sets, does the function have an inverse? And the answer is yes. How do I do that? Well, I set y equal to the function. And then I get this. And now I'm going to solve for x in terms of y. So you multiply both sides by 6x minus 2 plus 3. And then I get 6xy minus 2y plus 3. That's not working right. What am I doing here? First of all, I want to say you don't have to. I just wanted to explain what this notation means. You don't have to write all this down on the exam, like, oh, a minus b is defined as this, and then draw this picture here, and then explain, oh, the reason why we have to take this point out is because it's a point where the function is not defined. You don't have to explain any of that. I just wanted to explain what does this mean right here. All you have to do is say, yes, it does have an inverse, or no, it doesn't have an inverse, and then explain why. If it has an inverse, which it does in this case, find the inverse. And that's what I'm doing. And I'm making a mistake for some reason. I'm not sure why. So you set y equal to the function. And then you want to solve. Oh, okay, I see. Yeah, for x. So now I'm going to subtract 5x from both sides and then add 2y to both sides. And then I'm going to now factor out the x. So x times 6y minus 5 is equal to 2y plus 3. And then now I can divide that by both sides. And I get this. And then this, so now I can flip the x and the y, and that will give me the inverse. So f inverse of x is equal to 2x plus 3 over 6x minus 5. And notice the point, where is this not defined? Where is this function not defined? It's not defined at 5 over 6, because that will give me division by 0. Look at that's exactly the point we had to subtract out. Remember, if it has an inverse, if a function has an inverse, the domain of f is the codomain of f is the domain of the inverse. Well, this right here, oops, it's going crazy. This is just exactly the domain of the inverse. It's going to be the domain of this function right here. I have to take all, the domain will be all real numbers except this number right here, 5, 6. So the answer is yes, it has an inverse, and here it is. For the purposes of the test, you don't have to do the compositions, because that's kind of crazy. I won't have you do that. Maybe, yeah, I won't because just for the sake of time. If there is an inverse, I definitely want you to explain why. And so for the next part, it's going to turn out the function is not invertible. It does not have an inverse. So this is part, actually, let me just keep consistent notation. So this is part 4. So now we're taking G so of course, to talk about inverses, you need to specify the domain and codomain. It's important. We saw that with the x squared function, and that's exactly what we're dealing with. We're basically dealing with a variant of the x squared function. We're dealing with 2x squared. And since we're talking about the whole real line, it's of course going to be far from injective. So I just take -1, 2, I just plug in -1 and I get this. -1 squared is 1, I get 2, and I did plug in 1, I get 2, 1 squared, that's 2. Right there, that one single alone, that calculation alone implies that G not injective. So if, for example, you could even have done -2, so that would be 2, and -2 squared, so it'd be 4, that would be 8. And then G of +2 would be 2 times 2 squared, and again, +8. So this, you don't have to do both calculations, do one, but I just showing you that there are a lot of values. There are at least 2 values where you can see that the function is not injective. So the answer to this part is that no, does not have an inverse. So that's the whole exam. Of course, if some of this still doesn't make sense, come see me during office hours. You can email me, or you can go to the tutoring room if you need further explanation or whatever. For the test is basically going to be this. You basically just took the test. Like here and there, I changed numbers, of course, but all the problems are basically the same. Like this one, I described different transformations. I gave you a piecewise defined function. I gave you another value. Instead of evaluating at 3 points, you have to evaluate at 4. There's a completing the square problem like this. There's a parallel line problem. It's just the same. So if you know how to do these, you understand the methods, you should be fine. Because I also don't want you to just throw an answer down. You need to justify. You need to go through the steps, or most of the steps. I pointed out where you didn't have to write down everything that I wrote, because there's a lot of background explanation I was giving, but you have to give a reasonable amount of details. So but the test is going to basically do this. For this last one, I just want to say now for the last one, be on alert for, like, know your basic graphs of x squared and x cubed, and whether those are injective or not injective. So for example, x squared as a function from the real numbers to the real numbers is not injective, as we just saw. Well, we saw 2x squared, but basically the same calculation shows that x squared itself is not injective. But x cubed and multiples of x cubed, those kinds of functions are. So yeah, just know the graphs. You'll be able to tell from the graphs whether these are injective or not. And when you see a function, like if it's not clear to you whether it's injective, just plug in a couple values and see, like, and be on the alert for, like, does the function involve something like x squared? Does x squared show up? And if it does, then that should tip you off that something's up, that there's something amiss. So yeah, just understand, yeah, if you can do these problems and you understand them, and you're not just memorizing the the answers or the problems or whatever, you should be fine, because the problems will be a little bit different. But for the most part, they're all, it's the same type of problem with different numbers and yeah, just different numbers. So I think that's all I want to say for that. So just go through this, finish the homework and go through this practice exam and you should be fine. So let's stop sharing and stop recording.